Hello and welcome to another LeetCode video. Today we're going to be doing the problem of the day for July 11th, and it's going to be all nodes distance k in a binary tree. And so in this problem, given the root of a binary tree and the value of a target node and an integer k, return an array of the values of all nodes that have a distance k from the target node. You can return the answer in any order. And so in this first example, you need to get nodes that are 2 away from the target node, and it's this 174. And in the second example, you need to get all nodes that are 3 away from the target node, and there's only 1 node, so you want to return the empty array. So how would you do this? Well, it's actually pretty straightforward, and so I'll explain to you why that is. So let's draw this example. This is one we're going to be working with. Okay. And so you want all nodes that are k length away from a target, but the problem is, like, once you're down here in a normal tree, you can't go back up and you can't like check nodes that are over here, right? In a normal tree, you can only go down and you can recurse back up, but you can't like go from here to here, go from here to here, and so on. But think about what would happen if I was to say, imagine this isn't a tree, but this is a graph with undirected edges. And you can go wherever you want. Well, now it's a pretty straightforward problem, right? You would start at this node, and then you can just do a breadth first search to figure out what level you need to go to, and then once you get to that level, you can return the answer, right? And so in this case, if k equals 2, you would just go 2 levels away from where you're at. So you can actually transform a binary tree into a graph pretty straightforwardly. You just go down the tree, and for every single child, you just say, like, if there's a child, let's make a path here, and let's make a path here, and you store all those paths, and then you have a unweighted, graph that's bidirectional. And then all we have to do is just start at whatever node the target is, and then we just go from there. So imagine this is a graph, right? So let's say this is a graph. We're going to start at 5, and then it's a pretty straightforward BFS problem. So all you have to do is we're going to do a normal BFS, right? So we're going to put 5 into a queue. We're going to have a visited set, and we're just going to say until k is 0 or until we have nothing left to visit, let's just do a breadth first search. And so the way it's going to work is we're going to pop 5, right? It's in our visited set. We're going to pop 5, and then we're going to take all of the values that are next to 5, right? Breadth first search. So we're going to take 2, 6, 3, and we're going to add those to the visited set. So every single time we add something to our breadth first search, we're going to add those to the visited set. Now we went down a level, so now k equals 1 here. So we're not at k equals 0, and remember, these are all visited. So 6, 2, 3 are all visited. Because this is an unweighted graph problem, as soon as something is in your queue, it's guaranteed to get there before something else, right? So if you had like 2, 6, 3, 4, 3, you don't need the 3 twice because every node is only one length away. And so you can do that. So now we need to actually go down one more level. And so what are the children of 2? So it's 7 and 4. For 6, there's nothing left. Everything is visited. And for 3, there is 1. So we're going to add those to our visited. So 7, 4, 1. And now we have k equals 0. And so now we're at the right level, so we can just return this. And so that's essentially all we need to do is we just need to transform this into a graph and then do a basic breadth first search on how to get to the right level. And that's all there is to it, to this problem. So I'm going to show you in the code how we transform it into a graph and then how we traverse and how it works. So let's take a look. So we're going to make a paths that's going to be a default dict of list. And essentially, in a normal edges problem, you want to have a node and then you want to have a list of edges from it. And so we're going to traverse and we're going to say if there's a node left. So like for 3 and 5, we're going to make a node. We're going to make an edge from 3 to 5 and from 5 to 3. It needs to be bidirectional. And so that's what we do here. So we're going to make an edge here and then we're going to traverse down and it's going to be recursive, right? So if there's a node here, let's traverse down, let's keep going, and so on. And if there's a right node, do the same thing. Make an edge here, make an edge here. So from 3 to 1 and from 1 to 3, and let's traverse down. So we're going to go through the entire tree. We're going to make edges from every single node to its child and to the parent, so back and forth. And then finally, now we can check if the target is not in the path, because it's not guaranteed to be in here, right? Like let's say the target's 9, then it's not in here, so we can just return an empty array because it's not in there. So then we make a visited set with the target val, and that's the node we're going to start at. We're going to start at the target node, and we're going to go from there with a breadth first search. This is a standard boilerplate BFS template, and I like using this a lot. And so you just have while BFS and k is greater than 0 are your conditions for keep going. because if you have no nodes, then obviously you can't go down any more levels. And so this is a little trick to keep a level of a BFS. Essentially, if you use this for range loop, it will execute the number of times that the length of the current BFS. So if it's like 3 elements, right, when you call this will execute 3 times, even if you're adding more elements in the end. It takes a snapshot of how many elements there are when you call this, and it will execute that many times. So if there's 3 elements and you pop on 10 more, it will only execute 3 times for the first level. So this is a nice little trick to go level by level. So we're popping a node, and then for every single path in the pass node, right, for every single edge for the node, like for example, we pop 5, the edges are going to be 3, 6, 2. So we need to add 3, 6, 2 to our queue, but we only need to add them if they're not invisited. So if they're not invisited, we're going to add them to the path, and we're going to add them to the visited set. And then once we traverse down a level, then we're going to subtract from k. And then when k is 0, we're at the level we want, or when we have no more elements left. So if there's no more elements, we're going to return an empty array. Otherwise, we're going to return the level we want. And so that's essentially the code. And let's try to run it. But yeah, I think it's a pretty straightforward problem once you recognize it's a graph problem. And so let's think of the space and time complexity here. So for the time, so we do have to, what do we have to do? We have to traverse down the whole tree, so that's already O of n. And we have to make these edges, but that's just O of n. And then for this BFS, worst case scenario, it's O of n, right? We can just go through every single node, can't be worse than that. And then for the space, so obviously we have to make edges for every node, but you can only have so many edges, right? So because this is still a tree, I think you have like n-1 edges. So if you take a look here, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6 edges here. And this is not a completed tree, but yeah, I think worst case scenario for a completed tree, I think you have like n-1 edges, if I remember correctly. So worst case scenario, it's still not that bad. So every node is going to have n-1 edges. Sorry, not every node is going to have n-1 edges. There's going to be n-1 edges total, which means the space for this path is O of n, and then the space for this BFS is obviously O of n because you only have n nodes, and so space is going to be O of n here as well. And yeah, that's going to be it for that. So hopefully you like this problem, and if you did, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.